Hello, my name is Warren Hill and I'm a product specialist at Gasco. Gasco, in an effort to better educate our customers and add additional value, has developed a best practices training series. Our intentions are to better explain, better educate, and to ensure a helpful understanding of what gas regulators are and to discuss their normal operation. Gasco represents three major manufacturers of combustion gas regulators. They are Sensus Metering Systems, Pietro Fiorentini, and Maxitrol. In this series, we hope to answer any questions that you might have. If you have questions or require additional information, please feel free to contact Gasco toll-free at 1-877-427-7347 or through our website at gascoonline.com. In this regulator training segment, we will be discussing a term known as Droop, or set point deviation. Droop can be complicated to understand and how it affects the regulator performance. Many people confuse or think that pressure drop across the regulator and droop to be the same thing, when in fact droop and pressure drop are entirely different. Regulator droop is the loss of outlet pressure or set point pressure as the flow rate increases. The closer you get to the maximum flow capability of the regulator, the more pressure is affected by droop. Droop is an effect on the gas flow that is created by the sensing diaphragm, the range spring, and the internal body effects. If a manufacturer could construct an ideal regulator, the performance curve would look like the following, which would be a straight line curve. But as you can see, an ideal regulator would not be affected by the mechanics of the regulator. The horizontal axis at the bottom of the graph would show the rate of flow. The vertical axis would show the outlet pressure. As the rate of flow would increase, the outlet pressure would not change. The best way to illustrate or to understand how droop affects flow rate is to think of a garden hose with a pressure nozzle on it. As you squeeze the handle of the nozzle, the flow would continually increase until you reach a point to where you get the most flow with the most amount of pressure. If you keep squeezing the handle further and further, what happens? You will notice the pressure drops off, but the flow does not. A gas regulator works exactly the same way. As you approach the upper end capability of the regulator will start to sacrifice pressure to maintain flow rate. However, a regulator has some inherent design characteristics that do not produce the ideal curve. Droop is most evident and has the most dramatic effect in the last 20% of the flow range of the regulator. This is easily demonstrated by the following performance curve. So what is diaphragm effect? It's pressure acting on the underneath of the diaphragm surface area. The area of the diaphragm that is connected to the diaphragm pan does not change. However, the flexible diaphragm material around the perimeter of the pan will change the geometry to allow the diaphragm assembly to move up and down. So as the pressure under the diaphragm decreases, the diaphragm depresses, the flexible diaphragm stretches and the area increases. The pressure now is acting on a different geometry of area than it was previously. Therefore, the force acting up is greater than it would have been with the fixed area. The valve, therefore, does not open as much as it would have. The outlet pressure decreases as a result. The second reason for the regulator not to perform ideally is due to what is referred to as the spring effect. The spring will continue to open. However, as the spring opens, the coils are extending and the spring's force begins to diminish. The further it opens, the more it loses its force. Unfortunately, this is when the desired position of the valve is to be in a more open position. Yet the spring is losing its ability to more easily open the valve. The final adverse effect causing a regulator to deviate from an ideal performance is called body effect. Because of the way a regulator is designed, there are inlet pressure effects that comprise the body effect. The effect of inlet pressure acting on the underside of a valve, pressure acting on the underside of the diaphragm, and the changing surface areas due to the changing geometry all comprise the internal body effect. In addition, the gas is swirling and the turbulence as it makes its way out of the regulator and downstream also adversely affect regulator performance. Again, all these forces are additive and affect the total capacity of the regulator, resulting in approximately a 20% decrease of the maximum table value of the regulator. So here at Gasco, we always try and size the regulators so that we never operate within the last 20% of the maximum regulator capacity. If you have questions or require additional information, please feel free to contact Gasco toll-free at 1-877-427-7347 or through our website at gascoonline.com.